In this video, I will be reviewing the concepts of sampling distributions and confidence intervals. Suppose I was interested in estimating the mean recovery time for a particular surgery for a given population. To make this easier, let's say I wanted to estimate the mean number of days that it takes an adult male aged 50 years or older to recover from a particular knee surgery, and let's use an arthroscopic knee procedure. One way that I could do this would be to find every male who is 50 years or older who's had this surgery, find the number of days that it took them to recover, and found the mean. That is what I'm looking for. Now, what's the problem with this? It should be pretty clear. Finding every single patient who meets this description, who's had this surgery, is a male, and is 50 years or older, and then asking them about how long it took to recover, that's not going to be feasible. There could be hundreds of thousands of people who have had this surgery. Put another way, we cannot access the entire population. So what we need to do is to rely on a random sample from this population. Let's look at a simple simulation to see how we might be able to use samples to estimate the mean recovery time. On this page, what we are going to do is use a simulation. At the top of the page here, we see that we have a population of interest. And in this case, this is the population we want to estimate. We want to know the mean recovery time for males aged 50 years or older who've had this arthroscopic knee surgery. Notice we don't know what it looks like. That's why it's blocked off. So what we're going to do is we're going to take a sample of 75 individuals from this population, and we're going to see what the mean is. Now, I'm going to hit this button over here one time, and what you'll find is I will have 75 samples, or 75 individuals sampled. The mean of those individuals will be sampled, and that will be plotted. Let's see what happens. So to review, we see that 75 individuals, which is showing up right here in this histogram, were randomly selected, and then the mean of those individuals, in this case we're talking about the recovery time, was found, and that is plotted down below. So it looks like the mean was 37.6 approximately. Let's keep doing this. Let's take another sample of 75 individuals randomly from the population and see what we get. Here, I had another 75 sample, and now I plotted the mean. Let's do this again. And again. And again. What we're doing here is we're finding all of these samples of 75 individuals and looking at the mean duration time. Let's suppose we did this thousands and thousands of times, which we know is not plausible realistically. As we know, studies and randomly selecting 75 people, these things cost money. But since we are simulating this, we can do this randomly thousands and thousands of times. So I'm going to hit this button 1,000 times, multiple times, to see what happens. Let's look what we found. Down below, what we have is all of the samples. So we took 10,005 samples. Out of all of those samples, the mean of all of the means was 35.3672. And the standard deviation of all those means was 2.06 approximately. What's really interesting here is the shape of this distribution, which again is all of the means. Looks like a normal distribution. It looks like a bell curve, and that is not an accident. Essentially, what we're doing in this simulation is creating what's called the sampling distribution for the mean. In other words, if we were to take all possible samples of 75 patients, not just the 10,005 that we did, but all possible samples, found the mean and plotted all of their means, we would have what's called the sampling distribution for the mean. This is really important because it allows us to regardless of whether or not we know the population or not, or what the shape or the distribution looks like for the population, we know what the sampling distribution is going to look like. Now, this sampling distribution is a very important concept within inferential statistics and is the foundation for some very important statistical theorems. In fact, what's one of the most important, if not the most important theorem in statistics is called the central limit theorem. And that tells us this. If we were to take a sufficiently large sample size, and generally statisticians and researchers will say this is something greater than 30, we know that the distribution of the sample means will be normally distributed with a grand mean equal to the population mean and a standard deviation equal to the original population standard deviation divided by the square root of n. Now that's a lot to absorb, so let's go back to our picture and see what that tells us. Because we were able to use a simulation, we have the capability of removing this block here and looking at what this particular population looked like. Notice we were drawing from a population that had a mean of 35.35. And when we were repeatedly taking samples and looking at the mean and then plotting that mean, we can see down below the distribution of all the sample means is very, very close to that population mean, about 35.35 or 35.36. What the central limit theorem tells us is that as we continually take samples, this grand mean, the mean of all the sample means, will be approaching the population mean. It also tells us that there is a relationship between the original population standard deviation and the standard deviation or the disbursement among all of the sample means, and that was given to us by the formula. This standard deviation of the sampling means is also called the standard error, and it tells us approximately how dispersed all of the sample means are from one another. Okay, so we can see that the sampling distribution of the mean and the distribution of the population are related to one another. But how does this actually relate to confidence intervals, and how would we relate this to research applications? Well, let's go back to an example with the mean recovery time, and let's go back to the simulation. Now, I'm going to take one more sample, and notice I reset everything. We don't know what the population looks like, but let's take one sample. Now, I took one sample, and in the real world, this might be the only sample that I have, because we know that studies take cost, they take time, they take a lot of money, and we might not be able to hold multiple replications of our investigation. In other words, I'm not going to be able to continually take samples, find the sample mean, and construct the sampling distribution. So when I take this one individual sample, I don't know where it is relative to all other samples. I know it's somewhere on the sampling distribution, but is it going to be to the left of the overall grand mean or to the right of the overall grand mean? And how do I know how far away it is? This is where confidence intervals come in. So what we can do is rely on a very important property of normal distributions. If we know that some distribution is approximately normal, then we know approximately how far or what percentage of all the data values will fall within the overall mean. You can see in this picture that approximately 68% of the data will fall within one standard deviation of the mean. If you increase that margin so that we have minus 1.96 and 1.96, we're almost at plus or minus 2 standard deviations, we have about 95% of the overall data values that falls within this interval. If we consider all of the values that fall within approximately 2.58 standard deviations, this accounts for about 99%. This is how confidence intervals are constructed. If we randomly take one sample and we're unsure of where this sample is relative to all the other samples, what we can do is add and subtract a certain number of standard deviations to give us a little bit more wiggle room, to give us an interval that will include more values than just the sample statistic. So let's summarize some of the important characteristics of confidence intervals that we've seen so far. A confidence interval is an interval that we will use to estimate a population parameter, and these intervals are constructed with the following items. First, we need statistics from a randomly selected sample from that population. From our last example, we were using a sample mean. We were considering the mean recovery time for a knee replacement, but we didn't need to just use the mean. We could have estimated the standard deviation of the population. We could have estimated the proportion of the participants who had a complication or did not. We just were specifically relating this to the mean. We also need an estimate of the standard error, which we have found is the standard deviation of that sampling distribution. It gives us a measure of the sample error that we would expect with the statistic that we are calculating. Finally, depending on how confident we want to be, we're going to need a confidence level. The higher the confidence level, the larger the interval. If we want to be more confident that this interval contains the population parameter of interest, we better have a larger interval. So the higher the confidence, the larger the interval. All of this can be summarized with the following formula. And this is the formula specifically for estimating a population mean when the standard deviation is known of the population. This is what we were looking at over the last few minutes. We are given the sample mean. We see here this z alpha over 2. This is going to be determined by our confidence level. So are we going to add 1.96 standard errors or standard deviations? Or are we going to only add 1.6? Or are we going to add 2? Or are we going to add 3? The larger this number, the larger the interval, and the more confident we will be that our interval contains the population parameter of interest. And finally, this last piece here was our estimate of the standard error. These three things, the sample statistic, the confidence level, and the standard error, will all be different depending on the population parameter that we are estimating. If you're estimating a population proportion, or a population standard deviation or variance, or something different like a mean difference, or a percent change, or an odds ratio, all of these formulas will look slightly different. Let's look at a few examples of confidence intervals. The first example we want to look at comes from a study that looked at the volume of brain matter for two groups of individuals. Specifically, one group was the treatment group, which received a hydrocortisone treatment, and the other was a control group. In this table, we can see that the researchers were looking at the volumes for various parts of the brain for each of these two groups. If we were to consider the first row of this table, the cortical gray matter, we can look and see that confidence intervals were created to estimate the volume in the cortical gray matter for both the treatment group and the control group. In the treatment group, we see we have a range of 155 to 183, and this is in a volume, and we are told this is a 95% confidence interval. A correct interpretation of this interval would be the researchers have 95% confidence that the true mean volume for the cortical gray matter for the treatment group is between 155 and 183 milliliters. Now we want to be careful because there are really common misinterpretations of these intervals. Here's one. The researchers are 95% sure that the true mean volume of the cortical gray matter for the treatment group is between 155 and 183 milliliters. This is not correct. We are not 95% sure the true volume is contained in this interval, but rather we have 95% confidence in this interval. The difference is we only have, or the researchers in this situation only took one sample. And if they were to repeatedly take sample after sample after sample and create confidence intervals, then over the long run, 95% of them would contain the true volume. In the next column, we see for the control group, we have a confidence interval of 172 to 199. Finally, in the last column here, we have a statistic that we haven't seen yet, and that is the mean difference. This is a confidence interval describing the mean difference between these two groups. So we could say one has 95% confidence that the mean difference between these two groups, the true mean difference between these two groups, is between a minus 34, a negative 34 milliliters, and 12 milliliters. Mean difference is important because we can see that this interval contains 0, which might suggest if the mean difference is 0, there truly is no difference between these two groups. So in summary, we have 3 columns here. The first column looking at the mean volume for the treatment group, the second column looking at the mean volume for the control group, and finally the last column looking at the mean difference. For each column and for each row, we have an estimate of the volume and a confidence interval estimating the true population mean volume for each group. Let's look at one more example. This table was taken from an article, Health Status of the Prisoners in a Central Jail of South India. The researchers were interested in studying the prisoners for a particular jail, specifically their health outcomes. What was really important for their study, and is very common for other studies as well, is a description of the participants that they sampled. We see here that the researchers looked at the prisoners in this case, their age group, their sex, place of residence, marital status, educational status, type of family, and socioeconomic status. Now, the second column tells us the number of individuals from the sample that were in each of those particular categories, and the percentage in the next column. The final column is a 95% confidence interval, and this is being used to estimate the true proportion, or in this case, because it's greater than 1, it's been converted into a percentage, the true percentage of the group that is being represented. If we were to look at the marital status under married, we see 226 participants in this sample were married, and this was equivalent to 75.3% of the sample. Now, since this is one sample and doesn't necessarily speak for the entire jail, the researchers needed to estimate, or at least provide more information, about the overall prison population that is married. So they created a 95% confidence interval to estimate that percentage, specifically the percentage of married inmates. This interval, from 70.4 to 80.2, would be suggesting that the researchers have 95% confidence that the true percentage of individuals that are married at this institution is between 70.4 and 80.2%. To conclude this video, I'd like to provide a quick excerpt explaining the purpose of confidence intervals. This suggests that the purpose of confidence intervals is to give us, the researcher or statistician, a range of values in which to estimate a population parameter, rather than a single value or a point estimate. The estimated confidence interval, it gives us a range of values within which we believe, with a varying degree of confidence, that the true population value falls. Now we know that for a given confidence level, whether it be a 90, 95, or 99% confidence interval, that doesn't mean that there is a 99% chance that that interval contains that population parameter. But rather, given this unique relationship between the population and the sampling distribution, we know that if we were to repeatedly take samples and create confidence intervals, over the long run, 99% or 95 or 90, depending on the confidence level, a certain percentage of those intervals will actually contain the population parameter in question. This allows us to take a sample, create an interval, and estimate a population parameter.